Hello, this is Sean McGowan doing my video submission for Lab 8, Op-Amp Circuits with the Arduino. In this lab, we're going to be looking at various circuits we can use with our op-amps and various uses for the op-amps as well. So with that, we'll get right into it. Firstly, looking at the comparator we built, the intensity of the LED is low when the potentiometer input is less than 512 bits or 2.5 volts. But when the potentiometer input is higher than 512 bits, the LED is much brighter. As we can see from the graph provided in the lab, once our potentiometer input is greater than the 2.5 volts, the Vout will be then set to the 5 volts, which is supplied to the op-amp. And when the potentiometer input is lower than the 2.5 volts, the Vout is much less, thus a less intense LED. Next, we were to derive the gain of a non-inverting op-amp circuit. So first we start with our rule that V plus is equal to V minus, and since we can see that Vin is equal to V plus, we know that Vin must be equal to V minus. We then apply Kirchhoff's current law to determine the relationship between Vin and Vout. We then find the gain to be the factor of Vin, which in this case is R2 over R1 plus 1. Here we have our unity gain amplifier circuit, which is meant to output the same voltage as the input. We use unity gain circuits due to their large input impedances, which allows us to draw a very small current from the voltage source. The reason it doesn't match up below 1.9 volts on our graph is due to the fact that it's not an ideal op-amp. So above 2 volts, the graph is as expected with Vin, V minus, and Vout all equal to each other. Next, here's our inverting amplifier circuit. We were instructed to send a 2.5 volt signal to the non-inverting pin, so we used two 1000 ohm resistors to make a voltage divider. We were also instructed to have a gain of -10, which we accomplished by putting a 100 k ohm resistor in the R2 position and a 10 k ohm resistor in the R1 position. We then wired up the circuit to plot the Vin, V minus, V plus, and Vout over time in processing. We see the yellow dot, which is V plus, is a constant 0 volts input because it is not changing, and we changed the scale of processing to accommodate for the required 2.5 volts to the op-amp. The white dot Vin is being controlled using the potentiometer in our circuit. The V minus green dot closely follows our Vin, and our Vout dot inverts the input voltage. So when Vin is greater than 0, Vout will be negative, and Vin is less than 0, Vout will be positive. So lastly, we're looking at an integrated amplifier circuit. First, we're showing how we derive the relationship between Vin and Vout. The process is very similar to the inverting amplifier earlier in the lab. We look at the impedance for the capacitor, which is 1 over j omega c, and treat it as a resistor. We then apply Kirchhoff's current law, which to derive the relationship of Vout is equal to -Vin divided by j omega cr. Lastly, we show here our processing graph of the circuit. We can see that the circuit is an inverting circuit, which explains why Vout is inverted from the Vin input. V negative is different from the normal inverting circuit because it is a capacitor. We can see that it is charging up and discharging, going from 0 to positive 2.5 and 0 to negative 2.5. V positive is a constant 0 volts still, and the Vin is the potentiometer input. Alright, that's it for the lab. I hope you enjoyed, and I will see you next week.